On the assignments I graded, the main feedback I have is please, like anything that says, like all the things that say they're due February 24th or whatever, please attach those together in some way. Because, you know, like I have 100 students and lots of assignments and lots of tests. And otherwise, if it's like, I'll look at one and it'll only have half the assignment. And then like in some other pile, it's really hard to keep stuff straight. So if you could just paper clip them or staple them or something, but attach all the things that are supposed to be in on the same date. Okay, so we started rigid body kinetics. And there are two main equations for rigid body kinetics. The first one is Newton's second law. And it says that if you add up all the external forces on an object, that's equal to the mass of the object times the acceleration of the center of mass. And rigid body kinetics, I should point out again that this is 2D that we're doing. Newton's second law, this works perfectly well in 3D. The other one is the one that you don't want to approach the same way in 3D. The rotational equation. Okay, so this is the first one. The two most important equations in this class. That's the first one. And the second one says the net moment about a point A is equal to the moment of inertia about A times the angular acceleration, where A is either the body's center of mass or a point that's fixed in the body and the coordinate system. And both of these equations, in order to work, in order to be accurate, must be in an inertial coordinate system. So, for example, with that Atwood's machine, we saw that you would have gotten an error in the acceleration you'd expect if your measurements were taken in a coordinate system that was accelerating. Okay. What are the two ways a coordinate system can be non-inertial? Two ways. Yep. And rotating. Yep. So if the origin's accelerating or if the axes are changing orientation in time. So before we can use these equations, we need to define a few things. First, center of mass and the acceleration vector of the center of mass. Second, I sub A, which is mass moment of inertia about a point A. When I say the mass moment of inertia, that is to make a distinction, and this is a really, you know how kinematics and kinetics like are different things, and you hear those two words and you're like, come on, why? Like, why make it so confusing? Why don't you make them two different sounding words? Okay, so there is this variable capital I sub A in dynamics, the one that you saw in physics 1, that tells you how resistant an object is to being rotated. Bless you. And you call it, for short, you leave out the mass and call it the moment of inertia. In D form, there is a variable that you represent capital I sub A that you say, to save time, you call it the moment of inertia. And it is not this. It's the area moment of inertia, and it tells you how resistant a cross-sectional shape is to bending. That's a serious pain in the butt. So I'm going to try to, in both of those classes, bring out that distinction. But everything about them is the same. I mean, except what they mean. And then the third thing is M sub A. That's the moment of a force about a point. Okay, so once we've defined moment of a force about a point, about a point A. Once we've defined these three things, we can start using those equations. So first, the center of mass. And I'll always abbreviate that COM. And it's denoted or indicated on figures a lot of times this way. Have you ever seen that symbol before? What? Yeah, it looks like BMW. Well, actually, that wasn't what I was going to say, but it used to be on commercials, like car commercials. There was a period where everyone was really trying to show how safe they, and so like every car commercial showed crash test dummies. There were like ones that walked and talked, and there were images of crash tests and all this stuff. But on a crash test dummy, so it's this humanoid looking thing, and every separate part of the body has this symbol on it somewhere. And the reason for that is that if you're trying to figure out what kind of forces are being generated in a crash, you're going to look at this high-speed video and do all the physics of what's going on based on accelerations and velocities. And because the dynamics is so dependent on the location of the center of mass, in order to back calculate the physics, the forces from the accelerations, you need to know where the center of mass of each thing is during the video. So that's what that means. Well, so the different it could. I mean, they're trying to do. I mean, if they felt like it would, then they'd use a bunch of different sizes of crash test dummies, which I'm sure they do. I mean, I don't have any like information about that, but they don't show the center of mass of the dummy. That would be one center of mass here. They show the center of mass of the forearm and the arm and the upper torso and the head. And so from all that at any instant, so your center of mass changes as you So right now my center of mass is different than now, you know. And so, but if they know the center of mass of each piece, then at each frame of the video they can calculate where the true center of mass is. The definition of the center of mass is based on an integral, and it looks like I'm not even going to do an integral calculation. We're just going to use formulas that come from this integral definition. But the position of the center of mass is 1 over the total mass times the integral over the entire body. So let's say over the whole mass. The position of each infinitesimal part times the increment of mass. So you could use that to calculate. You could do computer approximations, numerical approximations of that if you don't have functions representing this stuff. For homogeneous bodies, what does homogeneous mean? People in D form, we've talked about this. Yeah, same material all the way through. So, so if you're talking about a steel disc or a wooden disc or something, then this holds. If you're talking about a disc that's half steel and half wood, this won't work. For homogeneous bodies, the center of mass is at centroid. And so in all cases in this class, we'll be able to calculate the center of mass based on the centroid. And that also is an integral definition. It looks pretty similar. The centroid you can think of as just the geometric center of the object. It doesn't take actual mass into account. In 2D, the location of the centroid, and we'll write it with a bar over the top, that's the indicator for centroid, is equal to 1 over the total area times the integral of the centroid of infinitesimal pieces times the infinitesimal area. And in 3D, if you thought about it for a couple minutes, you'd probably guess a way to generalize this to 3D, and the way you would guess is the right way. X bar, Y bar, Z bar is equal to 1 over the volume total times the integral. Oh, I forgot to give the boundaries here for the 2D one. This should be over the whole area. This one's over the whole volume. And it's the integral of X bar, Y bar, Z bar times the increment in volume. One thing that often simplifies centroid calculations is symmetry of an object. And there's a version of this for 2D and a version for 3D. In 2D, the centroid lies on any line of symmetry. So for example, if you're trying to figure out the centroid of this shape, it has a line of symmetry like this. So the centroid has to be somewhere along that line. And so if you know that the centroid lies along that dotted line, then you can just use the single component to calculate the x position of the centroid. That also means that if you can find two lines of symmetry, that uniquely specifies the centroid location. So for example, a rectangular solid has a line of symmetry like this, and a line of symmetry like this. And so the centroid has to be at the intersection. Circle that has a million, well, more than a million lines of symmetry. Pick any two of those lines of symmetry, and they intersect at the same spot. And so where those intersect is the centroid. And so we're going to be dealing with mostly simple shapes, a lot of rectangles. And so what this says is you never have to calculate the centroid location of a rectangle. It's just right in the middle along one axis and right in the middle along the other axis. In 3D, we're not going to do a lot of calculations in 3D, but in 3D, there's no such, well, it can be lines of symmetry if it's like a, revolution symmetry. I don't know what the words are for that. An axis of symmetry, right? But right, so the equivalent of lines of symmetry in 2D are planes of symmetry in 3D. So the centroid lies on any plane of symmetry. And so if you can find, it's not 2 anymore, we have 3 dimensions to specify, but if you can find 3 planes of symmetry, that uniquely specifies the centroid location. Okay, so what the symmetry stuff tells us is that for rectangles and ellipses and circles, we don't need any formulas for calculating the centroid. It's just at the middle. Okay. But for other shapes, I'm going to give you centroid formulas for a few of the simple shapes that we're going to use. And in D2L, there's a PDF in the same section that the syllabus is in that gives you formulas for all the shapes that we'll need. Yes. Yep. And really, I think on tests, we're going to pretty much always be using rectangles and stuff. But if you need it, yeah, I'll give it to you. Okay, so let me set up this table. So this is the shape, and this is just for 2D centroids. And I'll give the formula for the area and the formula for the centroids. The first shape is a quarter circle. Something like that. Notice that this does have a line of symmetry, so you could, this is a line of symmetry, and so you know that the centroid has to lie along that line, but I'm just going to give you formulas for the x and y position. So let's call this, so here's the centroid, and let's call this distance x bar, and this distance y bar. The area is just pi r squared over 4. Where this is the radius. And the centroid, x bar is the same as y bar. That's because they have to lie along that 45-degree line. And the value is 4r over 3 pi. And I guess the only other one that we're going to use in this class ever is a right triangle. So I'll call this distance h. And this distance w. And the centroid is there. So I'll call this x bar and this y bar. The area is base times height over 2. There's no base there. Actually, change that w to a b, like a normal person does. And then the centroid, x bar is equal, no it's not, because those are different. X bar is equal to b over 3, and y bar is equal to h over 3. Okay. So all we're going to use is quarter circles, right triangles, then rectangles, ellipses, and circles. And this is enough information to calculate all those. Now, that seems like a pretty restrictive number of shapes, but you can build up more complicated shapes by adding and subtracting these simple shapes. So there's a summation formula. that can be used to find the centroid of complicated shapes built up from these simple shapes. In 2D, the one we care about, this looks like the total centroid, x and y components, are equal to 1 over the total area times the sum over all the pieces. In this case, there are n pieces of the centroid of that piece times the area of that piece. And notice that this is just the finite version of the integral definition of the centroid. So in a way, this summation formula gives you a strategy for using that integral formula if you ever have to use it. This is the way to think about it. I'll do an example with that. In 3D, it has the pretty predictable extension of this. The total x bar, y bar, z bar is equal to 1 over the total volume times the sum of the centroid of the individual piece times the individual volume. This is the one that's going to matter to us. Okay, so let me do a 2D example. So let's say we have a shape like that. Where this is 1 meter and this is 1 meter. And the thickness for the whole thing is 0.1 meters. And let's say our centroid is down at this corner. And in that coordinate system, we want to come up with the coordinates of the centroid, of this whole shape. Well, I'm going to break it up into 2 pieces. I'll call this piece 1 and this piece 2. So I'm breaking it up into 2 pieces where if you add these 2 pieces together, you get the whole shape. And the coordinate system is down here. The centroid of piece 1, these are both rectangles. It's right in the middle of that rectangle. The centroid of piece 2 is right in the middle of that rectangle. Why did I put the numbers there? Okay. So we just have to figure out the centroids of those and then use the summation formula. I'm going to clean this up a little for the PDF. Okay, so this is piece 2. Its centroid is here. Okay, so what's the area of piece 1? It has a height of 1 meter and a width of 0.1 meters. We get 0.1 meters squared. And in that green coordinate system, what's the location of the centroid of piece 1? Yep. X bar of 1 is half of 0.1, so 0.05, right? That's how far in the x direction you have to go. Like you have to go 0.05 to here and then 0.5 to here. And y1 bar is equal to 0.5. So you can write it in components like that, or you can write it like a vector. And then for piece 2, the area is a little smaller because this length is only 0.9. So the area of 2 is 0.9 times the width of 0.1, 0.09 meters squared. And now how do you get from the origin to this centroid? Well, you have to go in the x direction over 0.1 to get to this edge, and then over 0.45 to get to the centroid. So that's 0.55. So x2 bar is 0.55. y2 bar, you have to go up 0.9 to get here to the bottom, and then up another 0.05 to get to the middle. So 0.95. I'll write that as a vector. X2 bar, Y2 bar is equal to 0.55, 0.95. A total is just what you get from adding those two up. So 0.19. Now the summation formula says X bar Y bar is equal to 1 over 0.19 times the sum of the area of 1 times its centroid. So that's 0.1 times 0.05, 0.5. Plus the area of body 2 times its centroid, 0.55, 0.95. And if you do that calculation,
1 over there, is that multiplied by that whole argument?
Yep, right. And if you go through that, I think you get 0.287, 0.713. So that means that on this shape, you have to go out x almost 0.3. You're off the end of this after 0.1, so it's out here somewhere. This isn't drawn to scale very well. And then you have to go up 0.713, which means you don't get to body 2. So the centroid of this shape is somewhere out in space. You know, it's not on the body. It's out here somewhere. Now, what do you use the centroid for? Well, we're going to use it because when we use Newton's second law, we're always talking about accelerations about the center of mass. Also, the weight force, you can always treat it as if the whole weight of the object is applied at the center of mass. So when you your weight vector into the problem, that weight vector originates at the center of mass. So this thing's weight is actually, it's like it's acting at this place where there's not even any material. Any questions about that? Yep. Oh, yeah. Sure. Those add up to 1. That's freaky. Subtraction works too. Like if you have a rectangular plate with a circular thing removed from it, you can do this all with subtraction. I think there's probably a problem where you have to do that, that you're going to be assigned. Right, so now what about the velocity and acceleration of the center of mass? Well, if you look at that definition formula, you can take the time derivative of both sides and so I guess let's think about the sum formula. Take the, ddt of both sides of the sum formula. And you get a velocity and acceleration equivalent of these that say the velocity of the centroid is equal to 1 over total area times the sum from 1 to n of the velocities of the individual centroids. Those shouldn't be 1s, those should be i's. Times the areas of the individual pieces. Yeah, imagine anything that's rotating, that has to be the case. Yeah, imagine a wheel spinning around in place. The center has 0 velocity. Right. That's right. The centroid is constant in a rigid body. Like the material point that it represents stays constant if it's a rigid body. But where that material point is in space isn't constant. As the thing moves, it goes through this path, and that's what the velocity is telling you. And then acceleration. looks just the same. 1 over the total area times the sum of the accelerations of the individual centroids times the individual areas. Questions about that? Okay, so that's all we're going to say about centroids. Now we can go on to the mass moment of inertia about a point. And I'm going to give this definition in 2D. In 3D, so in 2D, the mass moment of inertia about a point is just a number. In 3D, it's a matrix, a 3 by 3 matrix, but we're not going to get into that. If at the end we have time to go into three-dimensional body motion, then I'll define the matrix at that time. So the way you should think about this is as a rotational analog of the mass. So what does the mass do? In translational motion, you can think sort of loosely of mass as a resistance to motion. Well, you know, it's really a resistance to acceleration, but I think that'll do for how to store this in your brain. Likewise, in rotational motion, the mass moment of inertia about is a resistance to rotation. Well, if by motion I mean acceleration here. Resistance to rotation, I mean angular acceleration. But so, an example of that is, so like in gymnastics, you know, I used to do gymnastics. I was terrible, but I like it. I don't like doing it anymore. I'm too fat. Okay, but there's a guy doing gymnastics. He's doing like, say, a double backflip layout, they call it, you know, like his legs are straight and stuff. And here's another guy. Also doing a double flip, but this one's tucked, okay? You get a ton more difficulty points for doing the laid out double flip than doing the tucked double flip. And that's because this layout has, your body in that position has a very high mass moment of inertia. It's very hard to produce angular acceleration on an object like that. This has a low mass moment of inertia. So this is high mass moment of inertia. This is low. And that's why it's a lot easier to complete 2 flips tucked than it is laid out. And so intuitively, what the mass moment of inertia measures is how far mass is distributed from the axis of rotation. So the mass moment of inertia about a point measures how far the mass is distributed from the axis of rotation. So in this, in one with a low mass moment of inertia, the person's getting all of the mass of the body as close to the axis of rotation, in this case, its center of mass, as possible. Okay. Everything's just pulled in as tight as you can, and the tighter you can pull it in, the lower the mass moment of inertia goes. In this case, the center of mass is here, say, somewhere in the lower chest. You have the mass of the feet a full, meter or something away from the center of the mass. The big mass of the head is half a meter away, and so you almost couldn't get any mass further away from the center of mass than in this position. There's an integral definition for this. As far as the thing about, like, why do they make it so confusing? They call these moments of inertia both just moments of inertia when they measure different things, the moment versus the area. I think this acronym thing probably tells you why they just call them moments of inertia, because it's a mouthful to say. Why they call them both capital I sub A, that's a mystery. But so the integral definition for the mass moment of inertia. So this is for 2D mass moment inertia. About a point. I sub A is equal to the integral over the entire mass that M is for mass, not moment, of R squared dm where R is the distance from that increment of mass dm to the about point A. And so if you think about breaking up this body into a bunch of little infinitesimal masses, and then you add up the distance of each of those masses squared times the mass for each piece, calculate that for each piece and add it all up. In the laid out position, you get a big number. In the tucked position, you get a small number. Any questions about that? So like with the centroid, for the mass moment of inertia, we're not going to use this integral definition. That's the definition, but we're going to use formulas that come from it. And I'll go into those formulas next time.